All right. Welcome to today's Grasp on Robotics talk series. I'm Kostas Daniilidis, and I'm the faculty host for today's talk. You can find all previous talks on our YouTube channel and the Grasp website. If you're joining via Zoom, please submit your questions using the Q&A, and our panelists, Huang, Zhu, and Zhao Huilei will read from there after the talk, and they will pass also the microphone to the people in the room. I'm very glad to introduce to you Professor Qixing Huang. He's a professor at UT Austin. He's a graduate from Stanford, doing his PhD with Leo Gibas, who, by the way, will give the Grasp on Robotics talk on March 1st. He has done very foundational work on shape matching, and later also on 3D human pose estimation, on object pose estimation, and he was also co-author of the ShapeNet. He received the NSF Career Award. He received the award for the best data set at geometry processing and the best paper award at the same conference, and early career at the ITSCAI, I believe. And today he will talk about geometric regularizations for 3D shape generation.
Okay, thanks. Thanks for the nice introduction. So I'll talk about some of the recent ongoing research in my group. So we are in the generative AI era, right? So in my field, which deals with all kinds of issues with 3D data, a fundamental task is to learn a mapping that goes from a latent space to the space of like man-made shapes, space of deformable shapes, and space of 3D scenes, right? So such generative models have a lot of applications. For example, to solve inverse problems in vision, and to do shape exploration and data-driven shape design in graphics. So this field has exploded recently, right? Mainly due to breakthroughs in machine learning models. For example, in GAN, VAE, autodecoder, and recently diffusion models. So there's a common theme among those models, right? They all try to do distribution alignment that aligns the distribution induced from the generative model and the empirical distribution defined by the data, right? To apply those machine learning models in the 3D domain, we first need to solve the representation issue, right? So 3D representations. This is a very exciting area, and we pretty much have seen a lot of new representations, right? For almost all the 3D representations that we have studied in computer graphics, okay? We have at least one, sometimes we have a few polynomial representations. We also have representation like a triplane, which was designed for 3D generation. So this is very exciting, okay? But on the generative model side, I think this is next exciting, because what has happened so far is that whenever people design some machine learning model that is applicable to image generation, we take that model and pick a suitable 3D representation and apply that in the 3D domain, right? For example, we have 3D GAN, we have mesh VAE, we have the SDF applies autodecoder. And recently we apply diffusion models for shape generation. So the question here is that, is this what we can do, right? Personally, I think diffusion models are not really the ultimate solution to distribution alignment, okay? It's a very challenging problem because it's a very high-dimensional problem. Or we may have to do something else, right? So if you look at the difference between images and 3D models. For images, we have a very natural representation, and we care about visual appearance. Right, so if we do this distribution alignment of image patches at different scales, then we can generate very realistic images, right? So this is the reason why diffusion models in particular are very successful in image generation. But the problem is that in 3D, we care about a lot of 3D priors that we do not talk about, right, in 2D images. So what are those priors? For example, when you generate 3D shape, right, if you want to do manufacturing or 3D printing, those shapes need to be physically stable, right? So this is some attributes that we do not talk about mostly in image, right, domain. When you talk about deformable objects, right, so we have some underlying articulated structure, right? So those things we do not talk about in images. And then we also have topological priors, right? For example, if a shape is not connected, right, when doing implicit shape generation, that is not good, right? We do not talk about those into the images. So if we just do distribution alignment, right, because the network does not really enforce those properties, right? So there's no way you can preserve these priors, right? So my work is to study how to enforce those priors when doing 3D shape generation. So I will cover 5 papers in 3 categories. I will start with some ongoing work on enforcing physical and geometrical priors for 3D shape generation. Okay, so this is a paper under review. Now I'll go in deep about enforcing deformable deformation priors for deformable shape generation. Okay, so this would be the focus of this talk. Then in the end, I will talk about also some paper under review on enforcing topological priors. Okay. Okay. Yeah.
Are you really thinking of a constraint, or are you?
So that depends. Okay, depends. This will become clear. So
That's a soft thing, and it can be learned by a model that doesn't actually support, like model or model.
Right. So I will talk about that. Okay. So the big picture is that we somehow want enforce the prior during the training procedure. Okay, and how to do that is not trivial. Okay, that is what I'm going to talk about. Okay, so this is a paper under review. So the idea here is that we want to train 3D memory shape generators under diffusion by making them aware of the physical stability. Okay, I will have a specific definition of physical stability. Okay, so diffusion models are very successful. Okay, in the image generation. They beat games, right? And I think this is the current state of the art in generative models for many tasks, right? So this was introduced for image generation, right? The idea is that you start from a random image, then you denoise, right, to make the image sharper. One issue when applying this diffusion models to the 3D domain is that you have to keep the ambient dimension, right, of the diffusion procedure. And this is not easy to do, right, because, for example, for implicit shape generators, we don't know how to do that. Then 2 years ago, we have the latent diffusion paradigm, right? So essentially, you can train a decoder, then you do diffusion in a latent space, right? Then in the 3D domain, people realize, oh, this is very good, right? We can fix the implicit shape decoder and train the diffusion in a latent space, right? Which does not depend on the shape representation. Then a lot of people followed, okay? And I think I counted that about close to 100, okay, papers using latent diffusion for 3D shape generation, okay? So the teaser of those papers, okay, all look amazing, okay? But if you run the code, right, you realize a lot of issues, right? Because, for example, those are some of the geometry shapes, right? We have a lot of geometric and physical issues, right? For example, some of the shape geometries do not look very good, and there are a lot of holes. Some of the shapes have very thin structures. Some are not connected. They're not physically stable. Okay, so the issue here is that if you train a diffusion model, right, during the training procedure, you only see the latent codes of the training instances, which are very sparse, right? And if you extrapolate, the decoder does not really understand, right, the physical properties of synthetic shapes. Okay, so for example, if we have a pre-trained decoder for any latent code, through the decoder, we know that whether this latent code corresponds to, for example, a connected shape or not. We can also evaluate its physical stability, right? So essentially, we can develop a quality checker that evaluate the feasibility of a latent code, right? So if we can instill that property to train the diffusion model, we can do a lot better. And this is the goal of this work, right? So I want to talk a little bit about some relevant work called guided diffusion using a classifier. This has been explored in the image domain, right? So this is a well-known paper. And people apply this, for example, for deformable shape generation, right? To make the geometry shapes to be physically aware, applying essentially, so those guided diffusion deals with the diffusion procedure, right? Deals with the inference procedure. And to do that, there's a trade-off between fidelity and diversity, right? If you enforce those properties during inference, then you sacrifice distribution alignment. And also, this is very limited because you need to have gradients of the classifier, which is not easy to do. For example, for physical stability, those kind of attributes. So what we want to do is to look at the training procedure, right? So to enhance the training procedure of the diffusion models. So to do that, so what we want to do here is to have a quality checker. I will talk about how to define the quality checker later. Once we have a quality checker, we can define and normalize the density function between 0 and 1, okay? So if we have a G5, which is a pre-trained decoder, with the quality checker, we can define for each latent code a 0, 1 score. Okay, so this is a continuous one, okay? In contrast, the training samples they're discrete, okay? Okay, so that is what we want to do, and we want to use this density function to train the diffusion model, okay? So what we do here is to use the EDM framework, which I think is still state-of-the-art for training diffusion models. That paper has several contributions. One contribution is that you can decouple the training procedure and the inference procedure, right? You train the model better, and you can also improve the inference, right? They're somehow separate. So we focus on the training procedure. Okay, so this is EDM framework. So we extend this to having two distributions, one coming from the data, which is discrete, and coming from the regularization, the quality check, which is continuous. The central task here is to determine the trade-off parameters, right? How to use those two two data sources, okay? Right, essentially the trade-off parameters, okay? So the D is essentially the denoised network parameterized by a UNet, okay? So we want to determine the trade-off parameters in the front of the data losses. To do that, we look at some very simple problem. For example, if we have two independent random variables, x1 and x2, right? And they have variance. And then you solve a fitting problem to fit x to those sources, right? And you want to minimize the variance of x, right? So this is what you want to do, okay? And we know that then the trade-off parameter is essentially the inverse of the variance, okay? So essentially under this analysis, what we can do here is to quantify the variance of those two terms. This is not easy to do if you just look at this equation, but we all know that from score matching, if you optimize each term in isolation, then we know that the optimal denoised network actually matches the log gradient of the distribution, okay? So what we can do here is that we can measure the variance, right, of the log gradient with the ground truth, right, distribution. We can quantify this, right, using this as a guidance to determine the trade-off parameters, okay? So we prove that, for example, for data, so the variance is all 1 over sigma to the order power of 4, right? So this is easy to understand because if the sigma, the denoising scale is very small, because the data distribution is very sparse, okay? Then the distance to the ground truth distribution, the underlying continuous ground truth distribution, should be very, very large, okay, very large. But when sigma is very big, right, so they all goes to Gaussian distribution, right? So this is, so the variance is becomes smaller, okay? So this is also true if we do simulation, okay? Now, yeah. Right. But I want to have the understanding of the asymptotic behavior. So here what I do is that I take a mixture of Gaussian distribution. I know the ground truth. I sample from that. Then I do this smoothing. Then I measure, right? So, but in practice we don't have the underlying ground truth, but we can have this result. Okay. And for the quality checker, it's the other way around, right? So we have a constant term because there's a bias between the quality checker underlying ground truth distribution. But for very small sigma, for example, if the ratio between the regularization and the ground truth is smooth, okay, it's not 1, right? Because 1 is between 0 and 1, the other is not. But if the quality check is very good, if it's smooth, then this constant is small, okay, it's small. But we don't know these constants. But at least it means that in a small sigma regime, we can use the quality checker more than the data distribution, okay? So that is the main message. And how to set that in a principal manner, we can use this, right? So this is the idea, okay, the formula to set the trade-off parameter between different sigma, okay? Of course, we have 2 hyperparameters which we need to determine for different data sets, okay? Okay.
When you say P, divided by P data, you really mean the fraction is smooth?
Yeah, right. And we don't know how smooth it is, right? So this is true for very small sigma. We don't know the constant, but this is the insight. Of course, how to set it. For example, if the quality checker is very, very bad, then pretty much we have to make C ratio to be very, very small. Okay, we do not trust that. But in terms of the how do you set up the trade-off for different sigma, we can follow this. Okay? And if we compare this to what people do for without the quality checker, so they set up the nominal data to be 1 over sigma squared. Okay, this is understandable because if we want to decode the details, right, you have to give more ways to the denoise network at very small sigma, right? Otherwise, you cannot decode the details. So in our case, because we have a quality checker, the sigma will come from the quality checker. Okay, so we can set a constant for the data type. Okay. So of course, we also need to determine all the hyperparameters. I'm not going into details. The message is that without the quality checker, those hyperparameters recovers those of EDM. Okay. So I also need to talk a little bit about how to define the quality checker. So for the 3D shapes, in terms of the geometry, okay, the local feature patterns, we actually learn a neural network to predict the quality of a shape. So when talking about this, most of the people say that you are just doing GAN, right? Because GAN uses a discriminator. This is very similar to discriminator, but actually it's not, right? Because for GAN, all the synthetic shapes, they're bad, right? All the training shapes, they are good. So in my case, I want the neural network to differentiate good synthetic shapes and bad synthetic shapes. This can only be achieved by learning from labels. Okay? But the message here is that for the features that differentiate good and bad synthetic shapes, those are middle scale and low small scale features. And we can learn this from like 55 labels with 55 categories. They generalize well to other categories and also generalize well to other shape generative models, or that all those use implicit decoder. Okay. For physical stability, we actually do structural analysis to quantify whether a shape is stable or not, right? So this is one way to define physical stability, right? So structural stability, right? You can also use humans or simulate the shape that is stable or not by falling on the ground, right? So that is what we do not do. Okay. So there are many ways to quantify physical stability. And we also use a neural network to predict the structure stability from the eigenvalues of the stiffness matrix. Otherwise, performing this structural analysis is very time consuming. Okay. We also do a little bit more, right, to avoid decoding a latent code using a decoder, which is also time consuming. So I will skip this. Okay. So we evaluated this on the ShapeNet data set. In terms of FID and FPD and KPD scores, which are extensions of FID and KD in the 3D domain. So we get about 20%, okay, improvement compared to the state-of-the-art, which are very encouraging. And we also evaluate how much we get in terms of the physical stability and the percentage of connected shapes, right? So this is encouraging that in terms of physical stability score, because of training shapes, right? Some of them are very physically stable, some of them not, right? They have very thin structures. We cannot go from like 0.7 to 1, right? So the training shape has 0.81, right? So using this, we reduce the gap by 58%, okay? And also doing this parameter optimization accounts of about 30% of improvement, okay, which is also very important. Okay, all right. So we see improve diffusion model, we can condition the diffusion models on image input and on text input and on image input. Okay, we also have improved performance. Okay, so this is first work. Of course, there are many things we need to do. Any questions? Diffusion or the quality checker? Checker the essential shape net code, like 55,000 shapes. And we have about the similar size synthetic shapes. Generally from some shape generative model. And we also use it to label what are the good and what are the bad ones. Right, so we tried all the strategies, for example, using the cross labels to train a classifier and hoping that if you have synthetic shape, then if it's good, then the cross distribution is peaked, otherwise flat. But this did not work. So we have to use human labels on the good and bad synthetic shapes. Right.
So for your manual label, if we threshold the label, we can have threshold of 2.5 and then
so we have like 4 scales, 4 scales, like very good, good, bad, very bad. But it's 4, right? Not continuous, but the quality checker returns like from the neural network returns a value between 0 and 1. Right? Yeah. Okay, so we'll talk a little bit about more math, okay, for the rest of the talk. Okay, so this is the reason why I chose to talk about the man-made one first. So I'll talk about LRAP rec. So the idea here is that we want to, the previous one we focus on the latent diffusion, and the remaining ones we focus on the decoder, right? We want to train better decoders. For deformable shapes, we want to train use auto decoder VAE, right? And the graph decoder is a graph neural network applies to a latent code, right? And generates a 3D shape. Okay. So if we just do distribution alignment, okay, because the network does not really understand the underlying articulate deformation, okay, you get smooth interpolations, but the interpolations do not really preserve the part structure, right? So we want to improve the decoder so that the decoder preserves those structures. So one way to do this is to improve the network architecture. Why I want to mention this here is that I know that because there's, right, you have a lot of random walk in the equivariant space, right? So which, for example, preserve the rigidity, okay? One way to extend is to preserve articulate deformations, but this is a very difficult way to do. So another way is to introduce some regularization. Right, so motivation is that all networks are over-parameterized. So the message from the community is that if you train the network well, by designing losses, the networks will have different behavior. For example, if you train an implicit function, well, then it can go from non-feature preserving to feature preserving, right? And then you look at foundation models, right? So they trained from large scale data, and you do not change the architecture, you fine-tune the foundation models domain specific data, right? Then the models will have different behavior, okay? So it means that if we train the generative models better, then they will behave differently, okay? So this is what we want. We want the network to really understand the underlying part structures, okay? To do that, we need to have a deformation model, right? So what we did here is not very advanced. We use a AIP deformation model, which enforces that if we have a mesh, the deformation in the one neighborhood is vision, right? So this is a widely used deformation model for solving inverse problems. For example, in the computer vision community, what we do here is that whenever we have a reconstruction, we want to enforce the deformation between that reconstruction and some template shape, right? Is AIP, okay? Okay, so this certainly improves the performance to some extent, but the problem here is that, for example, if you look at the simple shape space, right? So we have a very large shape variation, right? Which is not really AIP, right? If we enforce, for example, the deformation between a fat person to the template is AIP. Locally, we have the scaling, okay? And sometimes we don't, it's not really even a similarity transfer, right? So it's not really AIP, okay? So what we did in this work is to really looking at a shape geometry model from a submanifold perspective, right? So the latent space provides a parameterization of the submanifold. So with that, if we have a geometry shape GC to Z, we look at small perturbation in the latent space, we get a perturbed shape, right? So the deformation between them is small, right? So what we can do here is to enforce the AIP between adjacent synthetic shapes. And this makes a lot more sense, right? But also it makes the formulation easier because in the original AIP formulation, we have to optimize rotation needs to optimization problem that does not have a corresponding solution, right? Back in 2009, I looked at the AP from the deformation in the infinitesimal regime, but of course at that time I did not expect this can be used to train a geometry model. This was done when I was a PhD. So in the infinitesimal regime, we can parameterize the rotation using a linear transform. Okay, one minus symmetry matrix. If we have that, then we have a quadratic approximation of this AIP deformation, right? So this HR matrix is a sparse matrix, and J is the Jacobian, okay, of the geometry model, okay. Then we can enforce the deformation between adjacent synthetic shapes using this HR bond matrix, which is a D by D matrix, to develop regularization laws. So we did a little bit more because, as I mentioned, right, so there are two types of variations. One is pulse variations. Another is shape variation, right? Pulse variation, okay? Those are captured by small eigenvectors of this H matrix. They correspond to directions in the tangent space that have very small deformation energy, right? Those deformations are just across the boundaries of the points, right? For shape variations, we have deformation everywhere, okay? So that corresponds to large eigenvectors. If we want to enforce this, we want to penalize this, those shape variations that are not really captured very well by the deformation model. So here we use a robust loss, okay? Then we add the fact that the other regularizations. And here we also assume that the training data have predefined correspondences. I will talk about how to compute correspondences later, okay? Okay, so we did some evaluation on 3 data sets. We achieved state-of-the-art results. Not surprising, otherwise we cannot publish this paper. But the message here is that for different shape decoders, okay, geometry models, adding the regularization, okay, which does not depend on the latent architecture, adding regularization all help. So that is very encouraging. Okay. So visualization-wise, adding regularization preserves the articulated deformation structure when performing deformation. Okay. Okay. So the second paper, I want to mention a little bit about this. I'll focus on one part of this, is to use this deformation model to design a latent space. Right? So what I mean is that this deformation model, soon after we published this paper, we realized that this HR matrix, which is a D by D matrix, is actually a Riemannian metric, okay, of this sum manifold. Okay? This is very nice because this, first of all, is an extrinsic Riemannian metric, and it's a pullback matrix of an extrinsic deformation metric. Okay, in the image community, people did study image generative models from the perspective about differential geometry. But the problem is that the image space is not really doesn't really have a nice manifold structure because we have discontinuities across different object categories. But the deformable shape space has a nice manifold structure, okay, which I think this is very important. And also in the shape space community, people also studied shape space from the perspective of Riemannian geometry. A line for Vogt studied the so-called Sobolev matrix, right? But those are intrinsic, okay? They do not really model the articulate deformation well. For example, if you have cross deformation, right? So that is very good, but it doesn't really model part structures, okay? So for that, we do need those kind of extrinsic metrics. So what we want to do is to use this Riemannian metric to do latent space design. I will focus on geodesic interpolation, okay, which is the most exciting part. So why we want geodesic interpolation is because, for example, if you have a Riemannian metric and you use that to do shape interpolation, to do shape morphing, we want this interpolated path to follow geodesic curve. Okay, this is true for most of the papers that study shape spaces. Okay. Okay. So the issues with existing latent spaces, the shape generative models, is that if we do linear interpolation, right, it's smooth, right? It doesn't really follow geodesic. Even after regularization, it does not. Okay. But if you ask them to follow geodesic, you get better interpolations. But you have to solve so-called PDE, right, which is very costly. Okay. Now the question here is that, can I just make the linear interpolations in the latent space, which is the most popular way to use a generative model, right, to follow geodesic curves? Can we do that? Can we do that? The answer is no. Okay. The answer is no. Not surprising, right? So it means that the metric is constant, right? It means that in Euclidean space. The proof, to my surprise, is not easy. Okay, it took me about like a couple of weeks to really put this in a rigorous manner. Okay, you had to write out the PDE, then express that using Fourier basis, and show that most of the constants are zero. It's not easy. Okay, so this is not possible. Then you quickly realize that you cannot even enforce that the interpolations within the two-dimensional subspaces are geodesics, right? Applying this theory, it means that all the off-diagonal entries are constants, right? Then the matrix is also a constant matrix. So two-dimensional subspaces, right, are not feasible. What we can do? We can reduce the dimension further, right? We can ensure that the interpolations are axis aligned, right? And later, for example, if we do post-shape disentanglement, if we enforce the disentanglement locally, then because we have axis aligned geodesic interpolation, then the disentanglement generalizes along different axes, right? So this is also a nice property in that regard. So the motivation of this comes from some previous work I did in the graphics community, right? By parameterizing a shape using the so-called geodesic wrap. So essentially the outside lines are geodesics. Okay, so this can be achieved through local parameterization. That's for that. So we can develop some regularization laws. So some of the result, for example, this is designed geodesic interpolation. Without the regularization, you get smooth interpolations, but they do not deviate from the geodesic interpolation. With the axis aligned geodesic interpolation, we get very close geodesic interpolations. Not exact, but close, okay? And so this is another example, okay? So we also did a little bit of evaluation, right? Do people really want geodesic interpolations in a latent space, okay? If we have a linear interpolation, okay, in mind. The message is yes, okay? For most of the cases, we do want linear interpolation to follow geodesic interpolations, okay? But we also did a little bit of post-shape disentanglement. So I will skip this using also using the matrix, but I will skip this. Okay. So I want to mention a little bit about this, right? Because I think this is what I call high-dimensional remaining geometry. Because if we talk to people working in graphics and vision and looking at physics, so the instance of there have a low-dimensional latent, no latent dimension, right? Below 6 dimensions, right? In physics, I think the Calabi-Yau manifold is 6 dimension. But for deformable shapes, right? For example, the simple model, we have like close to 100, right? So what is high dimension? Because the curvature tensor is O to the D to the powerful, right? You cannot even store the curvature tensor, right, in memory, right? We need to do, so I think this is a very exciting area, right, to make curvature regularization possible, okay, for shape generative models. Okay. The other way to do this, I think, is to make matrix sparse, right? But there are all kinds of issues, right? Whether this is possible or not, right? So this, I think, is very exciting. Okay, now I want to talk a little bit about how to compute correspondences using shape generative models. Right? So far, we assume that the training shapes have predefined correspondences, right? So this is okay if we study the geometry of shape generative models, but it's not okay if we want to learn this from raw data, right? We do need to solve the correspondence problem, right? And this is, of course, a very challenging problem, and I think it's still not solved yet. A standard way to do this, right, is to develop the objective function, right? You solve the optimization problem. This worked if two shapes are very similar, but it does not work if you apply the algorithm to less similar shape pairs, right? There are two reasons. One is that you have to solve a non-convex problem. There are lots of local minimums. But even you find the global minimum because you don't know the underlying deformation, right? You don't know this global optimal is the one you want, right? So this is a challenge, okay? Of course, you can learn this from data, okay? Learn this from data, okay? But still, this does not apply to other distribution data, okay? The one way to bypass this issue is to use joint shape matching. This is a problem that I have worked on for over a decade, okay? So I just give you one example here to understand context, right? So idea here is that if you have two dissimilar shapes, right? You insert an intermediate shape or multiple intermediate shapes in between, right? You apply the same algorithm to pairs, adjacent pairs along this path, right? Within shape, you solve an easier problem. You get better correspondences. They compose them together. You get improved one, right? So that is the idea, okay? But of course, you may say, oh, there's some drifting issues, right? But in practice, there's this improved result, okay? At least you avoid some local minimums by doing so, okay? Okay, so the main parameter here is that you first do pairwise matching as an initialization. Then you ensure that the maps are consistent, right? For example, cycle consistent to remove bad maps, right? So this is exciting. I think a lot of people follow this. And also you can apply this to train neural networks. And this leads to a cycle gap, for example, okay? But there's still some challenges, right? So first of all, to do this, you need a lot of training data, right? You need a lot of data so that it provides interpolations between these similar shapes, right? So the performance improves when you have more data. Right? The second one is that pairwise matching and joint matching are decoupled, right? This is suboptimal, right? The joint matching doesn't really understand what is going on in pairwise matching, right? And third one is that you need to encode all shape maps. This is not good if you have a large shape collection and you want to, for example, this is also not easy if you want to add a shape, right? So all kinds of issues, all those issues can be solved using a generative model, okay? So what we do here is that we just train a generative model to feed the training shapes, right? Feed the training shapes and use the generative model to induce pairwise correspondences between the training shapes, right? If the generative model feeds the training shapes, we can map the training shapes to the corresponding synthetic shapes. Because the generative model, if we use a mesh, they have correspondences. Then we get correspondences between all training shapes, right? Okay, so this provides a very good way to encode correspondences. It's very easy to add a new shape, right? Because you just solve a reconstruction problem using generative model, right? And this is not easy to understand, okay? But this also unifies joint matching, right? Because joint and pairwise matching, because joint matching naturally is enforced using the generator, right? And if you enforce some prior deformation prior on the generative model, right? Essentially what you do is that you apply the deformation prior to solve the shape matching problem between adjacent syntactic shapes, okay? Intuitively, you can understand it this way, okay? We unify that. But of course, because this joint matching is applied for all these synthetic shapes, okay? Not just training shapes. We solve the data issue, right? Much bigger than the number of training shapes, okay? All good. But still, we have to solve the initialization issue because if you train an explicit generator to raw shapes without good initialization, this is not going to work, okay? We cannot avoid this issue, okay? We cannot do this using a mesh generator, but what is really the representation that does not require predefined shape correspondences? Right? We use implicit shape generators, right? So this is the pipeline. It's a little bit complicated, but I think this is easy to understand, right? So what we do here is that we first train an implicit generator from the training shapes to extrapolate discrete samples into a continuous shape space. But of course, we want to enforce some priors on the implicit shape generator, which I will talk about, so that the shape generator is nice. Then we use the interpolations induced from the implicit shape generator to guide the template deformation, right, to align the template shape to all the training shapes to get initialization, okay, using the continuous implicit shape generator. Then we fine-tune the mesh generator, okay. So the bottleneck is how to train the implicit shape generator, right? So to do this, we combine data loss with two regularization losses enforces on the implicit shape generator, right? So that the interpolations preserve part structures, okay? Okay, so how to do this? If we want to enforce deformation pairs, we still need to solve the correspondence problem. But in this case, we only need to solve the correspondence problem between adjacent implicit shapes, okay? This is easier to do. And this problem is ill-posed, okay? So in the graphics community, people look at this, okay? For example, if you, in the level set, okay, representation, people started this. The challenge here is that implicit representation provides you one constraint, okay? A standard way to avoid this degenerate solution is to enforce that the correspondence is along the normal direction, right? That is what people, for example, when performing physics simulation do, okay? But this is not good because, for example, if you have a translating a rotating sphere, if you perturb the point in the normal direction, you are not going to recover, okay, the underlying transformation, right? Okay, so what we do here is, since we have a deformation parameter, we know the correspondence need to satisfy, and we have a constraint, right? We just solve optimization problem, right? To optimize the correspondence, right? So that they minimize some deformation energy and they satisfy the implicit constraints. Okay? This leads to a sparse linear system, and we have a closed form solution. Okay? Closed form solution, but you do only need to solve a linear sparse linear system, which can be prefactorized. Okay, allows efficient computation. So using the correspondence, we have a locally explicit parameterization, right? That is very similar to the mesh generator case. Then we know how to enforce the prior, okay? Okay. Then we can also enforce some cycle consistency loss, okay, on the correspondences among triplet, right? Triples of adjacent implicit shapes, okay? So combining together, we get improved interpolations using the implicit shape. So you use self-developed implicit shape generator, which also applies to deformable shapes. But without regularization, you get smooth interpolations, but those do not preserve articulate deformations. Okay, with the regularization, we get improved interpolations. Okay. Okay, so this is another example. Okay, once we have this, we can get smooth interpolations between the template and all the training shapes, and use this interpolation to guide a template matching, okay, which gives us initial correspondences. Then we fine-tune the generative model using those initial correspondences by enforcing deformation. So this really applies to the what I talked about at the very beginning of this session. Okay. Okay, so some quantitative evaluations. We first of all, Jordan matching techniques, okay? Several, even using functional maps, okay? And we also beat unsupervised deep neural networks that is applied to shape match, right? So I think we have a disadvantage here because we did not use any intrinsic features, right? So for example, if we have a training shape, right? We have a self-interpolation. We cannot do this because, right? So the shape generator is extrinsic. But the intrinsic features, you can still do this, right? But still we beat them. But of course, Another message is that all the regularization methods, okay, in particular, without regularization, this is not going to work, right? So all, for example, using the cell consistent loss also improves the implicit shape generator. Okay? Right. Okay, the last part I want to briefly talk a little bit about topology, okay, how to make generative models to be topological topology aware, okay? So there's still some issue. I still want to use this slide, right? So for implicit generative models, we also have a lot of topology issues, right? Holes, disconnected shapes. In topology is very different from geometry, right? Because topology is a global property, right? Connected or not. But geometry, right, we care about local property, local geometric feasibility. Okay. So this is also complementary to physical stability, right? Because if you have a lot of small holes, it's still physically stable, okay? And this was the reason why we actually incorporated geometric feasibility in the first work, right? Because without that, we cannot avoid small holes, okay? That can be learned from data, right? To do that in a more principled manner, we have to introduce topology here. Okay. So to enforce topological attributes, we have to use some topological tools. So we used a well-established topological attributes called Poisson diagram, right? So I think if you're working computational topology, you should know this, right? So this was introduced 2 decades ago by Herbert Isselbrunner, okay, which has made a huge impact, okay, in the computational community, okay. So simply put, right, what is a Poisson diagram, right? So we have a filtration of the topological space. Well, in this case, is essentially the height field, right? The function, okay? We caught the sublevel set of this, right? We check the burst and depth of topological feature, in this case, a local minimum, local maximum, okay? So the Poisson diagram is a 2-dimensional point cloud, right? Each point corresponds to a local minimum and local maximum, okay, in the filtration, okay? So in the 3-dimension, right, we have 3 Poisson diagrams correspond to 0 order, first order, second order topological features. They correspond to point cloud, right? And those point clouds are generated by a filtration of a 3-dimensional space, right? So some of the facts about Poisson diagrams, each PD is a 2D point cloud based on filtrations of topological spaces. If we want to apply this to implicit shape generators, so what we do here is that we use the 0-level set, okay, the sub-level set of the implicit function, right? So implicit function typically is a sign distance function, okay, sign distance function, okay, that is widely used, right? So each point corresponds to a pair of local and maximums of the sign distance field, okay, right? So this work is also motivated from some reasonable ones that use Poisson diagrams to do shape optimization, right? So idea here is that if you have a shape with some function, okay, on the shape, you have some priors about what the Poisson diagram of this function should be, okay? They can optimize this function so that after optimization, the Poisson diagram of the optimal function matches the PDE target you described, right? This leads to, okay, right. Okay, so this has been applied in shape reconstruction from point samples, okay? Okay, so if we use Poisson diagrams to quantify the issues of current implicit shape generators, they do implicit generation in the function space. If we measure the distribution, right, distance in the Poisson diagram, the distance is very, very big. Okay. Okay. So our goal is to train an implicit shape generator so that the distributions they align in the Poisson diagrams. Okay. Right. Also, the Poisson diagram, essentially the Poisson diagrams change smoothly and the PD distribution align. Right. Right. So the one issue challenge here is that can we do this just by regularizing the implicit shape generator? So in fact that if you're working in the, okay, give me 2 minutes, okay? If you run looking into computational topology, you know we have this stability theorem that essentially says that the bottleneck distance of Poisson diagram is upper bounded by the distance in the functional space. So in fact that if you just make the function implicit shape generator smooth, when you vary in the latent code, you get improved regularization. Okay, but this is not does not really apply to chilled. For example, we have a very large geometric topological variations. So what we do here is to train a point cloud decoder. Okay, that and do the interpolation in the Poisson diagram space, right, which leads to significantly improved distribution alignment property, right? And we use the point cloud generator to provide guidance to train the implicit shape generator. Okay, right, that is training loss. And this leads to improved generalization, okay, improved generalization, okay, right? So we compare to a bunch of baselines, and we improve in particular in terms of PD distance, we improve a lot. Geometry is comparable. Okay. Okay. Syntactically is also better. Okay. Okay. To conclude, I think I introduced a bunch of 3D shape geometry models that by enforcing priors, I do think that this problem is very different from image generation. Okay. And this is a field where machine learning and computer graphics techniques synchronize. Okay, there are many problems to work on. Right now, I think my group is working on how to make the decoder to be physically stable. Okay, the first work started latent diffusion by fixing the decoder. Okay. So I want to thank funding agencies and 2 of my students who actually did the most of the work. So I'm happy to answer questions.
Thanks for the great talk. And we first take the in-person questions for now.
Very interesting mathematics. Thanks. I have one question. So I guess the theme of this work is to develop a latent space of shapes. The complexity of the latent space, the metric, for instance, or the dimensionality depends on the diversity of objects that you would like to map. Elephants can become chairs if you are very creative. So do you have a thoughts? I wanted to understand how you think about what objects can be mapped and what objects could not be mapped.
Right. So that is actually very good question. So one answer is that we think the shape space, okay, is no dimension, right? So we think the shape space is no dimension. And is that really true? We don't know. Okay, we don't know, and because we don't know how the shapes, right, in our physics world are generated. But if you think about how the memory shapes are generated, right, they are designed by applying some software like, right, so this kind of through interactive modeling. Those softwares, right, if you use them, right, you model, right, so they have a finite set of parameters to do, right? The dimension of those parameters, right, I think it's not that high, right? You have parts and you have different types of parts, and then you have the choice of like free-form basis, right? So all the man-made shapes were designed in this way, right? If we are able to recover those parameters, right, through training, which I think is low dimension, right? It's much lower than the ambient space. Okay, I think we can believe that this may work. Okay, but we don't know. And of course, the latent dimension varies a lot across different categories. But we don't really have this for organic shapes. Okay? For many of the, for example, plants, animals, we don't. And that is my answer to this. Right? But certainly we'll be very far away from recovering the underlying parameters for all the memory shapes, like making them really like reverse the engineering. Okay, right. So we are very, very far from that.
So Qixing, a very interesting mathematical formulation indeed. So what can you say about like stuff from 10, 15 years ago, like functional maps? Pretty much when we were, spectral decomposition would really help in most of the stuff, including like synchronization or like cycle consistency. And so do we have really experiments where we show their deficiency compared to like latents that you generate with a generative model?
So in terms of the shape matching problem, I think function map essentially is a representation. Okay, the cycle consistency idea is orthogonal to that. But why I like this generative model idea is because this gives us a way to really understand what is really the limit of this joint shape matching, which I'm very interested because it has a continuous formulation and which allows us to quantify the limit using some geometric tools. I'm thinking about that. And I also think that, for example, the function map representation could be useful to develop efficient regularization. But I think that is somehow orthogonal to this generative model idea. With the function maps, if you develop, it allows you to learn from data, okay, so that the map generalizes to in-distribution testing data. But for us to also out of distribution data, you cannot do, right? That is not a representation issue. And this generative model idea is something that I think orthogonal to representation, right? So that is what, so I'm very interested in that because finally, I think there's a way to really answer. So what is really the limit of joint shape matching, right? So I think there must be some way to, my understanding is that the limit should be quantified in terms of the curvature of the shape space. The curvature is related to the deformation model we use, okay? For good deformation model, the curvature is small, right? Maybe using function maps, the curvatures become very small, Okay, so that is my intuition. What kind of result we can get? Without curvature is all cycle consistent. Right.
Do you have a opinion on whether like Gaussians will obviously pick poses that are closer to the center, and then obviously distances are not preserved if you map to a Gaussian space? So do you have an opinion on using a Gaussian in your VAE as your latent space, or versus like a maybe like a manifold, like as like a level set of a
So whenever we have a way to sample the latent space, we can use, right? So the regularization applies to any predefined latent distributions. But that certainly is a good question, because what we have observed is that enforcing the latent space to be Gaussian somehow competes the regularization, okay, or feeding the data. Right, and the regularization doesn't need a predefined prior space. Otherwise, we cannot know where in the latent space to enforce the regularization, right? So that is a challenge, right? But certainly that is applicable to any predefined latent distribution.
More high-level questions.
Yeah.
Like this is really nice. We have the properties that goes from the latent space to the geometry we generated, and most of the talk is about how to enforce this by some regularization losses.
Right.
What do you think about on the other way by construction?
Right.
Yes.
Right. So that is something that, for example, when I talked to Hongyue, right, I really encouraged her to look into that, right? Because if you want to extend that, the equivariant stuff to deformable shapes, that is natural extension. I think enforce the prior is easier, okay, than develop the new networks, because, for example, I don't think we know how to design new networks that generates, in all the cases, connected shapes under the implicit shape representation, right? And also, another argument over there is that you do not need to really explicitly design the network to enforce that property. For example, okay, if you train the generative model on the different representations, so the network architecture of those representations incur implicit regularizations, right? Because you want to minimize the magnitude of the network weights. That is the implicit regularization, right? Induces through the optimization procedure. And those effects will be different on the different representations. So I think it is still valuable to develop representations that people believe can promote certain properties. Okay? In fact, that is what in computer vision people do, right? And you do experiments, and you show that this network is aware of certain properties, right? Then the implicit regularization of the training procedure promotes that. Okay.
Yeah.
Right.
Oh, yeah. Sorry. Right, this concludes our talk. Thank you very much, Qixing.
Okay.
I have a script here. Yeah, please tune in on next Friday, the 16th, again, where we are hosting Guillaume Sartoretti from NUS, the National University of Singapore. Have a great